Hello, we are Aerojet Rocketdyne Remote Controlled Rover Payload, Group 21. Our advisor is Dr. Felix A. Soto Toro. Welcome to our Critical Design Review. Our group consists of Christopher Kiefer, Joel Marquez, Anjali Padmanabhan, and me, Chase Walker. So the motivation of this project was that our sponsor, Aerojet Rocketdyne, wanted to fund students to make a project for entry to the FAR rocket competition. This competition consists of a rocket and payload that will work together to reach the competition goal. Our goal is to create a reconnaissance vehicle payload, or remote-controlled rover that transmits live video, and we chose this goal because we are very interested in the implementation of the wireless communication and remote control. So we have four main goals and objectives that are powering our motivation. So first is to create a payload that will mate with a 10,000 foot IREX spec rocket and deliver a rover to the ground. Second is to create a rover that will operate via remote control and will transmit wireless video to the launch station. Third is to create an autonomous rover and capsule mating system for security. And finally, all systems will be designed for battery powered so we can have unhindered mobility. So our three main requirements for this system are that our live video will be transmitted at 480p 24 FPS during the mission. The rover will be able to turn 360 degrees in both directions and move forward and backwards. And finally, the rover will be able to travel a minimum distance of 10 meters from its landing site because this is a requirement in the FAR competition rules. Now we will give you a brief overview of the rover, the capsule, the rover control station or RCS, and the total system.
The rover chassis will be a light aluminum frame that mounts the PCB, video camera, motors, and the power supply. Rubber tires with aggressive treading will be used for the movement system to allow the rover to avoid terrain hazards. The power supply for the rover chassis will power the PCB, camera, transmitter, receiver, and motors. A rechargeable LiPo battery cell will be used to avoid recurring costs and keep vehicle weight down. The PCB will control all the remote control reception and translation operations, the video transmission, and the rover auto start system. The capsule and rover are to be mated using an electromagnetic coupler. The PCB will be responsible for sensing when the capsule has landed and for releasing the coupler to allow the rover to begin its mission. It will have its own battery and will be electronically disconnected from the rover. Rover Control Station. This controller and video receiver unit will be freestanding from the rover. It will have its own rechargeable power source to allow it to be moved freely. It will have and display the wireless video signal from the rover in 480p. It will have a joystick used to control the movement of the rover via radio transmission. The capsule will be loaded into the rocket airframe with the rover inside. The rover and capsule systems will be powered on and will be waiting to detect liftoff. The rocket will lift off and reach 10,000 feet before descending. During this time, the rover and capsule will detect this and start checking for landing conditions. The capsule will be ejected from the rocket via parachute at 1,000 feet. When the capsule lands, it and the rover will detect this, and the rover will be released from its coupling to the capsule and drive itself out. At the control station, it will be seen in the video reception that the rover is out of the capsule, and the rover will be piloted for a minimum of 10 feet to complete the mission. Member responsibilities. I will be in charge of the rover and capsule design as well as the manufacturing. Joelle is overseeing the video transmission system and PCB design. Anjali is overseeing the remote control system and PCB design. And finally, Chase is overseeing the power system, sensing systems, and PCB design. Here is the overall block diagram with the rover capsule system communicating with the control station. Here is the capsule block diagram. The rover block diagram. The rover control station block diagram. Rover chassis design. The rover chassis is designed to be fit within a diameter of approximately 14.5 centimeters, which is the maximum theoretical diameter to be able to fit inside the rocket payload bay. It is also designed to fit the large electrical components. There is a small cutout on the front of the rover to house the video camera. Note that a new CAD model is currently being produced, and that this one shown here is old. Rover chassis manufacturing. The rover chassis is to be manufactured out of 6063 T5 aluminum alloy. The aluminum pieces are going to be cut, welded, and fitted together. There will also be included anchor points for electrical components inside the rover chassis. Reinforced rubber housings are going to be used for the motors. The required tools include but are not limited to a plasma cutter, blowtorch, and power drill. Capsule structural design. Capsule is designed with key geometry features that allow for successful upright landings. The scoop feature on the front of the capsule guides the capsule to land on its landing gear after initial contact with the ground. Planned force balance within the payload will induce an angle of attack with the purpose of landing the capsule in the proper orientation. Capsule structure manufacturing. Similar to the rover, the capsule will be made out of 6063 T5 aluminum alloy. This aluminum will be cut and welded together to form the capsule. An eyelet screw for the parachute anchoring point will be attached towards the rear of the capsule. Rubber C-clamp will be used for securing the capsule door. The capsule door hinge is going to be purchased and connected by fittings. The railing and sled are to be machined out of aluminum by the manufacturing lab. Again, the required tools include but are not limited to a plasma cutter, blowtorch, and power drill.
All voltage regulators used in this project were developed using the TI Weebinch software. For all three schematics, each one has a 3.3 volt and 12 volt regulator. And these systems are all powered by 3.7 volt LiPo batteries. So 3.3 volt circuit uses a buck boost topology and provides a maximum current of 0.75 amps. 12 volt circuit uses a boost topology, provides a maximum current of 1.75 amps. These currents are determined by the maximum currents across 3 boards plus 250 milliamps of overhead. For the power supplies, we had the following calculations to figure out what size batteries we needed. For the capsule, we determined we needed 800 milliamp hours, rover 6 amp hours, RCS 3 amp hours. And here are the batteries we chose. We went with the 1 amp, 3 amp, and 6 amp hour battery, respectively. So for battery charging, we chose the MCP73833. This is a really common battery charging circuit. We're using a USB micro B as the power input for 5 volts from the wall. This is really convenient, and the battery will directly hook up to the circuit. And the circuit charges at 1 amps and has overcharge protection. Next, we have the landing system. So this system will be implemented inside of both the rover and the capsule, and it's used to detect the liftoff and landing conditions. And basically, this is used so since we can't see the rover and determine when it's landed and release it, it has to release itself. And this is how the system works. So when it starts, it will wait for a certain acceleration and altitude. We're using 4G and 600 meters in this diagram. And once it does this, it consistently checks to see when we have zero velocity and zero rate of change in the altitude. Once this is found, a 5-second timer is started, and those same measurements are constantly checked again. And as long as they are zero for this entire timer, we know that the capsule has landed and the rover can be released. We're using the following accelerometer and barometric pressure sensor to do our calculations. We chose these two because of their 3.3 volt friendly input range, and they both provide built-in outputs for their velocity measurements and the altitude measurements. And for the MCU, we chose an MSP430 FR6928 for all 3 boards. This is a 64-pin model because we don't need all 100 pins, and we chose this mostly because of our familiarity with the chip and its really easy ability to be programmed via an MSP430 launchpad.
Rover and capsule coupling. To prevent the rover from moving inside of the capsule during flight, a coupling mechanism was needed. An electromagnetic lock was chosen due to its form factor and high strength. When landing is detected by the capsule, the load switch connected between the power source and coupler will be opened to allow the rover to drive away. This lock is small, relatively light, and features a 150 kilogram holding strength.
The IC load switches used for capsule rover coupler control and motor control are shown here. They act as physical throw switches that can be controlled by an MCU GPIO pin. They're used to block the voltage to the circuits until we need them to be powered on. They use a series of MOSFETs to control current flow on demand.
Rover propulsion mechanics. This group originally decided to use tank track system to traverse the sandy, rocky soil expected from the launch location. Since then, the design has changed to utilize an all-wheel drive drivetrain with aggressive off-road style tires. The design was changed due to procurement issues and the mechanical complexity surrounding tank tracks. This all-wheel drive drivetrain is supported by 4 DF robot motors, which feature very high amounts of torque, perfect for traversing the rocky soil.
The 4 motors in the system will have their speed and direction controlled by the onboard MCU using PWM and GPIO, respectively. Each pair of motors, left side and right side, will share these signals. The motors and 12-volt power rail will be bridged by one load switch per pair of motors. This load switch will be used to cut power to the motors when they're not supposed to be moving. The system does need an auto start ability. Because we can't see when the capsule lands potentially, the rover will need to know that it's landed and been released, and it will drive itself forward to push open the capsule door, which will allow us to see via the live video feed that the rover is outside of the capsule. And of course, it does this using the landing sensing system described earlier.
Rover remote control joystick reading. The 2-axis analog joystick works by providing coordinate points of the joystick's position. Each axis's values range from 0 to 1023. The resting point of an unmoved joystick is 512, 512. Each coordinate will be classified in 4 levels required to move the rover. These include moving forward, moving backward, turning right, and turning left. The rover remote control communicates with the rover through radio transmission. The data from the joystick is transmitted through the radio transmitter, which is then received on the rover. The transmitter and receiver work in 868 to 915 MHz. It is required that the rover is controllable over a distance of 200 kilometers. The receiver on the rover will relay the information to the motors. Here we elaborate on the control schema of the joystick. First, we retrieve the dominant X or Y component value in the range 0 to 1023. If this value is less than 511, we set the direction as backwards or left rotation. If it's greater than 511, the direction is set as forward or right rotation. If it's exactly at 511 or the joystick is in neutral position, there should be no direction and the value is set to 0. Next, we evaluate the resulting component value to translate this into an integer between 0 and 10 to save that as a speed value for the motors. For example, if the joystick is pushed all the way forward, the x-axis will read as 1023. This means the motor should move at full speed at 10. These are the parts that we chose for the rover remote control. First is the RAYAX LoRa transceiver module, which we chose because of its long range of 15 kilometers and transmission frequency of 868 to 915 MHz. Next is the analog joystick because of its ease of use, and our team members are already familiar with this component.
For our wireless video capture, we decided to mount a first-person view drone camera onto the rover. The FPV camera chosen has a 155-degree field of view, which was decided to be enough information for the viewer at the rover control station. The camera captures at 700 TVL or 976 by 582 pixels. Video data is fed out in the NTSC format. Our video transmitter will receive the signal from the camera and send out the video signal along one of the 45.8 GHz bands the transmitter can choose from. The signal gets sent from the whip antenna of the transmitter to the receiving whip antenna on the receiver. The receiver then outputs the received signal via an AV wire. Our 800 by 480 pixel monitor will get its signal from the AV wire on the receiver. This monitor will be attached to the rover control station to give a live feed to the rover operator. Here are all of the parts relevant to video transmission. We chose a monitor for its relatively small size, its resolution, and the 12-volt input voltage. Our transmitter and receiver were chosen at a 5.8 GHz frequency for availability and because the frequency band does not interfere with other RF signals being used. The camera was chosen for its wide field of view, small form factor, and 5-volt input voltage.
Here we have the rover PCB schematic, which shares a lot of the same features as the other schematics. First, we have the power switch and LED, as well as 3.3 volt and 12 volt power conversion circuits. Next, we have the battery charger, which has the On the left, the USB micro B input and the battery charger output on the right side. Next are the motor power switches. The switches connect to the motor I/O pins, which have the PWM and direction signals. Below that, on the left, we have the remote control reception signal I/O and the video transmission signal I/O. Next are the accelerometer and altimeter shown on the top and bottom. And finally, we have the programming header and reset switch for the MCU. So this PCB, here's the layout. It's 7.1 centimeters tall and 11.5 centimeters wide. It's got 5 mounting holes, and the accelerometer is mounted near the center of the board next to the mounting hole for stability, which was required by a standard we will show later.
Here we have our capsule PCB schematic, which shares much in common with the rover PCB schematic. In common are the power switch, an LED, 3.3 and 12 volt conversion circuits, battery charger, microcontroller unit, programming header, and the altimeter and accelerometer. Unique to the capsule PCB is the rover coupler and power control, which allow for the automatic disabling of the rover coupler. Here's the layout of the capsule PCB. It is approximately 7.5 centimeters tall and 6.5 centimeters wide with 4 M3 screw mounting holes. Similar to the rover PCB, the capsule PCB, accelerometer, and altimeter were placed close to the mounting holes for stability.
Here we have the rover control station's PCB schematic. Similar to the rover and capsule's PCB schematics, we have a power switch and LED, 3.3 volt and 12 volt power conversion circuits, and a battery charging circuit. The main necessities of this PCB are the joystick header, the radio transmitter I/O pins, and then power for the video receiver and display screen. We also include an analog to digital converter for the joystick. Here's the final PCB layout for the rover control station. It will be 8 centimeters tall and 6.7 centimeters wide with 4 mounting holes on the 4 corners. Connections for the wireless video receiver and display screen are on the bottom right, and connections for the radio transmitter and joystick are on the bottom left.
The engineering constraints are as follows. Number 1. The payload capsule and payload must be able to withstand an impact speed of 3 meters per second. Number 2. The rover must be able to traverse desert terrain including sand and rocks. Number 3. The radio band of 420 MHz to 450 MHz is reserved for the rocket avionics. 4. The payload capsule and payload must be able to withstand up to 8 Gs when their drogue parachute deploys and during launch acceleration. 5. The payload, sled, and capsule assembly must weigh less than or equal to 4.31 kilograms. Number 6. The payload must be unaffected by operation in the radio frequency ranges of 420 MHz to 450 MHz and 1 GHz to 2 GHz. Number 7. The payload sled must take up no more than 1.2 centimeters on either side of the payload. Number 8. Payload dimensions must be less than 14.5 centimeters in diameter and 40.64 centimeters in length. Environmental and sustainability constraints. Litter and waste protections. This project was designed in a way that it will not create litter, and all parts used will be harvested after the mission. Rechargeable batteries were chosen to reduce waste, and one-time use technologies were avoided. Consideration was made for the way the sandy terrain of the target operation environment could impact the rover. Manufacturing constraints. Due to potentially harmful side effects of the manufacturing techniques used in this project, soldering, torch welding, plasma cutting, special care and safety measures will be taken to prevent bodily harm. The silicone shortage placed extreme pressure on both this team's ability to source parts and their budget. The increase in prices of the shortage, along with inflation caused by the team to go over budget with prices of multiple components increasing by 200% since fall 2021. Ethical constraints. This team explored ethical considerations when creating the design of the system to make sure no harm is done to their public. The conclusion the team reached was to keep the operation of the rover restricted to group members so the electronics aren't used without regard for typical ethical considerations. It was concluded that there will be hardly any impact on humans because this project will not be used commercially and will be used in a regulated environment. The team still maintained that ethical considerations regarding the environment mentioned in a previous slide.
For the safety of ourselves and for the rocket, we had to take extra precautions due to the general volatile nature of rockets. For the safety of the rocket, the team made sure to avoid using wireless frequencies that were being used by the avionics on the rocket. We also made sure our design was compatible with the rocket to make sure we don't damage the structure of the rocket. To ensure safety, our group confirmed with the rocket teams to make sure the use of LiPo batteries were safe for use. For the safety of everyone involved, we will also maintain a proper distance from the launch site. For sensor standards, we follow two regulations from the Code of Federal Regulations for the altimeter. Part 29.1303 of Title 14 says that altimeters should be sufficiently sensitive for the application. To follow this rule, we chose altimeters sensitive to plus minus 20 centimeters. Part 29.1325 says altimeters must be properly vented to the atmosphere during use. To follow this standard, our capsule design was purposefully made open and unsealed. We also followed a standard from the American Society for Testing of Materials, which says accelerometers need to be firmly attached to the chassis of the vehicle for accurate measurement. We adhered to this rule by placing accelerometers close to the mounting points on our PCBs. For working with the 5 GHz frequency, the FCC has some regulation about the amount of power and bandwidth you can use. The rules are to use a maximum of 300 megahertz of bandwidth and a maximum of 250 milliwatts of power for your transmitter. Our rover adheres to these regulations. There are also ASTM criteria to test whether a rover is effective and responsive at certain distances. Our team will borrow these procedures or derive our own from their criteria. Our programming language used to program the rover will be embedded C. This will be used in all 3 of our PCBs. We will follow Michael Barr's embedded C coding standards to maintain organization in the project code.
For video encoding, we will be using the NTSC format. The RCA, or Radio Corporation of America, phono connector is the display connector that is used to route the composite audio and video signal. In electronic communication and control standards, either I2C or TWI will be used for altimeter and accelerometer communication within the MCU. PWM will be used to control the speed and response of the motors for the rover locomotion. UART will be used to handle communication of transmitters and receivers with their respective MCUs. For connection and interface standards, the USB 2.0 or USB Micro B is used for the 5-volt input into the battery charging circuits on each PCB. JSD is used for battery, camera, and coupling mechanism connections. Provides a strong physical latching connection resistant to vibration. 2.4mm pitch pin headers or PCB connection holes are used for motor connections, programming pins, and power connections for the video transmitter, receiver, and display. These provide easy soldering and are a standard pitch for the male and female headers used in prototyping. Here is our current budget table. Our sponsor, Aerojet Rocketdyne, provided us with $500, which covered our initial purchases. Currently, we are spending out of pocket. In red are the parts that troubled us the most. This is because at the time of purchase, their prices had spiked to 3 times as much as when the part was first chosen.
Here's our current progress by subsystem. We're a little over halfway done with our entire project, with the subsystems broken down on this graph. So our main difficulties in this project so far have been the part shortage and the inflation caused by this part shortage. This has made us go over our sponsored budget, as you previously saw, and it's made acquisition of parts really challenging. We've also had some difficulties working with a separate team, which has just caused design changes to happen here and there. And then our little concerns at the moment are wireless video system is currently malfunctioning. We're not sure if we have a dead on arrival part or what the issue is, but we are working on it. For a future plan for success, the next couple of weeks we'll be doing assembly of our rover, capsule, and our PCBs. And then after that, we will test all of those together. Once we've tested our own system, we will integrate with the rocket and test there. And with those results, we'll make any last minute improvements or final testing.